All right, pre-calculus. Easy working microphone. Chapter 5.1, angles and their measures. We're going to talk about things with the unit circle. I'm going to move that cursor so that it's off the screen. Annoying. Positive angles always have a counterclockwise rotation. So we start on the positive x-axis, which you guys should have seen at least a little bit of this before. The positive x-axis will be your initial side. And then counterclockwise is the way that it goes. This would be your terminal side. And then this point, the origin, is your vertex. Looks like it says vertex, but I swear there's an R in there. Okay. So positive angles start at the positive x-axis and go counterclockwise. Negative angles start at the positive x-axis and go clockwise. So I still have my initial side and my terminal side. This would be a negative angle, my vertex, all that stuff is still in the same place. A positive angle that's greater than 360 is going to go all the way around one time and then go further than that, depending on how much further than 360 it is. So when it's like that, you can take your angle measure and subtract 360, and then that's where your terminal side is going to be. You're just going to loop around. It's like going around in a circle and then coming back. Because everything on these, like this, with the unit circle, it repeats every 360 degrees or 2 pi. So if I have an angle like this, but it's greater than 360, it's going to look like that. This is still my initial side, my terminal side. My vertex is still at the origin. Quadrantal angles, you know, the coordinate plane has quadrants. Remember, your quadrants are 1, 2, 3, and 4. Quadrantal angles are on the axes. So this here would be a 90-degree angle. That would be the first quadrantal angle. The second one would be a 180-degree angle. The third one would be a 270-degree angle. And then the fourth one would be a 360-degree angle. And we'll talk about those values on your unit circle in a minute. We've talked about all of these things. We're going to sketch the angles when it says to draw an angle, and a semi-accurate sketch is all I really need. It doesn't have to be anything perfect. 45 degrees is 45 is half of 90. So we're right in the middle there. Make sure that you have the arrow going the correct way. Positive 45 degrees. We start at our positive x-axis and go counterclockwise 45 degrees. Negative 90 degrees, so positive 90 would be here. So I'm going to do the same thing, just opposite. Negative 90 degrees will go this way. And it's going to be in the same place as 270 degrees positive. (225 degrees is 45 degrees past the 180, which is a straight line. So I'm going to go, I have my initial side here. Well, 180, 45 past that is halfway in between 180 and 270. Positive 225 looks like that. And then 405, I'm going to say 405 because it's more than 360, minus 360, and I get 45 degrees. So essentially, it's the same thing as A, but I'm going all the way around one time before I stop. So I'm still at that 45, but I have to go all the way around and then stop at the 45. Questions on this? Degrees, minutes, seconds. This is probably brand new to you. It should be brand new to you. It is how longitude and latitude are written, and it's really applicable, and I think it's really cool. It's called degrees, minutes, seconds. 1 degree is 60 minutes, and 1 minute is 60 seconds. This one apostrophe here means minutes, and the 2 apostrophes means seconds. It's just the notation. I think you know what the degree symbol means. 1 minute is 1/60th of a degree. So it's like it breaks it down into teeny tiny degrees. If you think about the world and it being a ball, and you have, and we'll look at a problem like this in a minute, but if you have like the world, let's say this is a nice sphere, and I'm no artist, but if we're here and from here to here may not look like a very big angle, right? But 90 degrees is like half of the earth. So whenever you zoom that in, you need to be able to get teeny tiny, and that's what these minutes and seconds do. It allows you to have that really long decimal without having that crazy notation. So it's pretty sweet. And we'll look at one that actually kind of brings that to life. So to convert from degrees, minutes, seconds to a decimal, your degrees is always going to be your whole number part. So you're always going to have that 50 or whatever your degrees is, plus 6 minutes. So I'm going to do some conversions here. I'm going to multiply that by 1 degree over 60 minutes, because there is the 1 degree is 1/60th. And then my seconds, I'm going to do the same thing, except for to get seconds in a degree, I have 3,600 seconds in a degree. Okay, so 3,600 seconds in a degree means I'm dividing this by 3,600. So your minutes can cancel there, your seconds can cancel, and everything is now in degrees. So in my calculator, I'm just going to type this. I've got 50 plus 6 times, and I'm going to say 1/60, plus 21 times 1/3,600. And I've got that nice, really exact decimal degree. And I'm going to round it to 4 decimal places. It will usually tell you if you have to round. So we have 50.1058 degrees. These calculators are pretty cool in that it converts from decimal degrees to degrees, minutes, seconds. So if I've got my 50.1058, I can go to my catalog, which is second 0, and then go down to D and have my, it says DMS. There it is, DMS. And it will convert it. So it's got that 20.88 because we had to round this 56.21.
Where is it?
So go to catalog, second 0, and then down to the D's. And there's like a little arrow and it says DMS. So this one, you can technically do that in your calculator. I'm going to show you. Did you find it? Isn't it cool?
Oh, well, that's cool.
Yeah, I know. Calculators are awesome. 20.256 degrees, minutes, seconds. So I like to go this way mathematically. I don't know why. I think it's easier to do this mathematically than to find the DMS in my calculator because it's so far down. So your 20, your whole number is always going to be your degree portion. Then I'm going to take my 0.256 and I'm going to multiply it by 60 minutes in 1 degree. So I'm canceling out my degrees and I'm multiplying my 0.256 times 60 and I get 15.36. The whole number, again, is what goes in your minutes. So I've got 15 minutes. Then I'll take that decimal, because this is minutes, and I'm going to multiply it by 60 because there's 60 seconds in 1 minute again. So now my 0.36 times 60 is 21.6, and I'll round there. So it'll be 22. So I think that multiplying each decimal part by 60.
But if you were to do it,
But if you were to do it, so you've got your 20.256, second catalog, down to D, EMS, there we go. If you were to write the 21.6, I wouldn't fault you for that if you didn't run that. So I like degrees minutes second. Questions so far? All right. We are going to look at arc length and eventually area, I think. Arc length, S equals R theta R is your radius, length of your arc, 1 radian. So a radian is another measure of angle measure, and it is in reference to the ratio of the circumference to the radius of the circle. I don't remember correctly the definition. Central angle is an angle whose vertex is at the center of the circle. So a central angle would be this angle right here, and this arc length would be equivalent to this angle measure. That's a math 3 thing that was, I don't know if y'all had math 3 last semester, it might have been cut out a little bit. S equals R theta, the only problem with this is theta has to be in radians. So this is a pretty simple formula, but your angle has to be in radians. So if it's not given to you in radians, and we'll practice some conversions here in a minute. Find the arc length when our radius is 2 and our central angle is 0.25 radians. So we're just plugging that in. I have 2 times 0.25. It's already in radians. And that is going to be 1/2 of a meter because we started with meters. Degrees and radians, remember the formula for the circumference of a circle is 2 pi r. So that would be sort of your arc length, but for your entire circle. Arc length formula, r theta, depending on, as long as theta is in radians. These are just some different values. How to convert between radians and degrees, and then some variables. These are Greek letters, and they're used a lot for angle measurement, and we'll use more of them as we move on and get into triangles.
what's
So-
the sign for radian? The little circle thing?
There's not actually a symbol for radians. Typically, if it's theta, it's in terms of radians. If it doesn't have a degree symbol, assume radians.
What does the S stand for?
S stands for your arc length. So to convert from degrees to radians, I have to multiply by pi over 180. Because there are 180 degrees, there's pi, they're equivalent to each other, pi radians and 180 degrees. So essentially, when I plug this into my calculator, you're going to say 60 divided by 180. If you plug pi in, it's going to round it. We typically want it in terms of pi. So 60 over 180, I want to simplify that fraction. It's 1 over 3, and I still have my pi on my numerator. So this is equal to pi over 3. $150, you're doing the same thing, multiply by pi over 180. So I'm saying 150 divided by 180 in my calculator and simplifying that fraction. I still have my pi on my numerator, 5 pi over 6. Because the only thing I haven't done when I type this in is also multiply by pi. If you multiply by pi, it's irrational. Decimal's going to go on forever. It's not exact. We want exact measures. Negative 45 degrees. Doing the same thing. Pi over 180. So negative 45 divided by 180, make a fraction. I get negative 1/4, which would just be negative pi over 4. And then 90 degrees, multiply it by pi over 180. And you get pi over 2. Do the opposite, convert from radians to degrees. Instead of multiplying by pi over 180, you'll multiply by 180 over pi. So now I'm saying times 180 degrees over pi. Your pi's will cancel out, and you can just type in your 180 divided by 6, which is 30 degrees. Typically, your radians is in terms of pi. You will see it sometimes where it isn't, like number 3 above, we had 0.25 radians. So your pi's will cancel, and that's the goal here. 180 degrees over pi. My pi's cancel, and I'm saying 3/2 times 180. Which is 270 degrees. Negative 3 pi over 4 times 180 over pi. Again, my pi's cancel, so I'm saying negative 3/4 times 180. Is negative 135. And then that last one, 7 pi over 3 times 180 over pi. You're saying 7/3 times 180, which is 420 degrees. Questions on those? All right, we're going to look at one of the degrees, minutes, seconds problems. Number 6, latitude is an angle formed by a ray from the center of the Earth to the equator and a ray drawn from the center of the Earth to the location. So what we've got here is we've got a nice circle. I'm going to try to make this look, oh boy, somewhat like an actual sphere. The center of the Earth is what's inside the sphere, the very center. And we've got the center of the Earth to the equator, and then a ray drawn from the center of the Earth to the location, so wherever our location is, if that's our place on the planet. So Glasgow, Montana is due north of Albuquerque, New Mexico. So we're going to say if this is Montana, we'll call this one New Mexico. Right there. Just some random places. Find the distance between them if Glasgow is 48 degrees 9 minutes and Albuquerque is 35 degrees 5 minutes. Assume the radius of the Earth is 3,960 miles. So to find the angle between them, that's what I want, is the angle here in between. And then I'm going to have to find the arc length, or the distance from here to here of that. So what I'm going to do is I'm going to find the distance between those 2 points, the angle between. I'm going to convert that to radians and then plug it into my arc length formula so I can find that distance, okay, along the surface of the Earth. So first, to find the distance between, or the angle between, I have my 48 degrees 9 minutes, and I'm subtracting my 35 degrees 5 minutes. 48 minus 35 is 13 degrees. 9 minus 5 is 4. So that is the measure of that angle. Before I can plug it into my arc length formula, it has to be in radians. So to get it into radians, I first have to convert it to decimal degrees. So convert to degrees. I've got my 13 degrees plus my 4 minutes, and I'm dividing that by 60 because there are 60 minutes in 1 degree. So in my calculator, 4 divided by 60, 0.06667. So I've got 13.066, I'm going to do 4 decimal places, 7 degrees. Now I'm going to take that degrees and to convert it to radians. So 13.0667. I'm going to multiply that by pi over 180. So 13, I'm going to put it back 4 over 60 plus 13. Now I'm going to take that and I'm going to multiply it by pi over 180. And I'm going to divide it by 180. So I have 0.0726. I'm going to say pi radians. And you can multiply it by pi and get another estimate. Or you can just not multiply by pi and plug it in at the end. Now I'm doing my arc length, which is my distance between those two on the surface of the earth. S equals my radius, which is that 3,960 that was given to us in our problem, times this whole thing, 0.0726 pi. Use your pi button anytime you plug it into the calculator. And you get 9.03. We're just going to round to the nearest mile. Or 9.03, 903, sorry, miles. So those two places are roughly 903 miles apart on the surface of the earth. I just think that's a cool problem because it's so applicable. Questions on that one? Area of a sector is like when you have that central angle and you found your arc length, but we're finding the area of that portion of the circle. This would be a sector. 1/2 r squared theta. Again, theta has to be in radians. So find the area of the sector of a circle with a radius of 2 feet formed by an angle of 30 degrees. So first I have to convert that to radians. So I've got my 30 degrees and I'm going to multiply that by pi over 180. Which when I plug into my calculator and make a fraction, I get 1 over 6. So I have pi over 6 radians. Then I'm plugging it into my formula for area of a sector. I have 1/2 my radius, which was 2 feet squared, times my angle measure, which is pi over 6. And you can just plug that straight into your calculator. 1/2 times 2 squared times pi over 6, which is 1.05 roughly feet. And this is feet squared because we're talking area. The last thing we're going to talk about on this chapter 5.1 is reference angles. Reference angles are the acute angle theta prime formed by the terminal side of theta and the horizontal axis. So it's the closest distance of that terminal side and the x-axis. Okay. So here, this example, this would be like 135 degrees if it's about 45 in there. My reference angle would be this distance here, which would be 45 degrees. Here, this would be like about 200 degrees, maybe roughly. So my distance here, my reference angle would be about 20 degrees, the distance between that and the closest x-axis. And if this is my whole angle, my reference angle is this small angle here. So again, it's acute. Remember, acute means it is less than 90 degrees. So we're going to find the reference angle. And sometimes it'll help you if you draw a picture. So 300 degrees This is 270 right here, so that's going to be 30 degrees away from 270. So if this is 30 away from 270 and this whole thing is 90, then you can say 30 minus 90 to get that acute angle, which would be 60. So you could say 360 degrees minus that 300 degrees because it's closest to this 360 degree axis, which would give you 60 degrees. This distance is 60.
I think it's
Because the whole thing all the way around is 360. So this would be 90, 180, 270, 360. So based on where it's closest to, so I chose 360 because I need the distance. That's the closest x-axis that it has. Does that make sense?
Yeah. If you do either of them, it has to be.
So if you chose this one over here,
Oh.
it would be not acute.
Okay.
Yes. Does that make sense?
Yeah.
So 2.3 radians, so your radians is going to be a little different, and we're going to look at your unit circle here in just a second. This is 2 pi radians, pi over 2 radians, pi, excuse me, 2 pi over 3. So 2.3 radians, pi radians is 3.14159, right? That many radians. So this is less than that. Pi over 2, if you type that in your calculator, pi over 2 is 1.57. So your angle is going to be somewhere in between here. This would be your 2.3. So what I'm going to say here, because it's going to be closer to pi than to 0, is I'm going to say pi minus my 2.3. And I'm going to round that. It's going to be about 0.84 radians will be your reference angle. Questions on that? So knowing that this is pi over 2, which is about 1.57, knowing that this is pi, which is about 3.14, I know 2.3 has to fall between those two numbers. So it's somewhere in this may not be exactly accurate, but it's somewhere in this quadrant. And if it's in this quadrant, then the closest x-axis is this one. So this would be your original angle. This is your,
leave it at radians?
Yeah.
Okay, so-
nope, you can leave it in whatever it's in unless it says specifically, which I don't think it will. And then the last one, negative 135 degrees. So we have negative 135 degrees. This would be negative 90 right here. This would be negative 180. So that's going to be 45 degrees in between the two. So what I can say is 180 minus my 135 because that is my closest x-axis. 180 degrees minus my 135 degrees. So even though this is negative, you can pretend it's not just to get your reference angle. And you're going to get that 45 degrees. Questions on those? All right, I think your unit circle is next in your packet. We're going to fill that out together.
No, it's after.
Okay, so let's flip to the unit circle and do that first, and then we'll go back to 5.2 because we need it. So to fill in the unit circle, I always start with degrees. I always do the coordinates last because to me that's more of a memory thing. Degrees and radians. If you make extra notches here, and you don't need to label everything for those extra notches in between your bigger gaps, then each notch goes up by 15 degrees. So only if you make this extra notch. Otherwise, it goes up by 30, 15, 15, 30. Okay. So if we start with 0 degrees, we go up by 15 degrees, and I'm just going to write that here just to kind of help you. The easiest way to fill these in is to go in the pattern as quick as possible. You will have a unit circle quiz. It's on the outline. I can't remember what day it is. But you will have a unit circle quiz just to fill it in without any notes from memory because this is not something that's given to you on like the final exam and things like that typically. And you need to know it. It's really helpful. So 0, 15, 15 more is 30, plus 15 is 45, 60. This one will be 75. 90. 105. Oh, no, sorry, that would be 105. I skipped one. 105 plus 15 is 120. 135. 150. I'm just gonna mark that out and rewrite it. 165. 180. I'm just adding 15 all the way around. 205. That's not right. 195. 210. 225. 240. 255. 270. 285. 300. 315. 330. 345. And 360. Questions on the degrees? So then my radians with these extra notches, my radians are going to go up by pi over 12. So I always start with my 0. And then this one is going to be pi over 12. The next one is going to be 2 pi over 12, which you should always simplify that fraction, which would give you pi over 6. So if you go up by pi over 12, you can just simplify the fraction each time and get the radians without having to convert everything. 3 pi over 12 gives you pi over 4. 4 pi over 12 gives you pi over 3. This one would be 5 pi over 12, which doesn't simplify. And then we would have 6 pi over 12, which simplifies to pi over 2. At 105, we'd have 7 pi over 12. Then we would have 8 pi over 12, which is 3 pi, or 5 both sides by 4, 2 pi over 3. 9 pi over 12 is 3 pi over 4. 10 pi over 12 is 5 pi over 6. 11 pi over 12. 180 would be 12 pi over 12, which is just pi. And we're just going to keep going around to 13 pi over 12 at 195. 14 pi over 12, which simplifies to 7 pi over 6. 15 pi over 12, which is 5 pi over 4. 16 pi over 12, which simplifies to 4 pi over 3. 17 pi over 12. 18 pi over 12, which is 3 pi over 2. 19 pi over 12. 20 pi over 12, which is 10 pi, divisible by 4, so I've got 5 pi over 3, sorry. 21 pi over 12. 7 pi over 4. 22 pi over 12 is 11 pi over 6. 23 pi over 12. And then 24 pi over 12, which is 2 pi. A lot of them. So then my coordinates, the radius of the unit circle is always 1, hence the name unit circle. We have 1 unit. So we can do our quadrantal points pretty simply. My radius here, I've got 1, 0. My point here would be 0, 1. At pi would be -1, 0. And at 3 pi over 2 would be 0, -1. And then the insides here, my middle angles are always √2 over 2, √2 over 2. You just have to look at what's positive and what's negative. In the first quadrant, x and y are both positive. So it's going to be √2 over 2, √2 over 2. And I can prove this to you someday if you want. But for now, sake of time, we're just going to push through. My other middle angle, again, is √2 over 2, √2 over 2. But my x is negative here. So I have negative √2 over 2, √2 over 2. My next middle angle, they're both negative because both x and y are negative. And then my 7 pi over 4, just my y is negative. So I have √2 over 2, negative √2 over 2. My other two on the outside, these are some combination of 1/2 and √3 over 2. The way that I always, honest to God, remember it is I make this a triangle and I sort of like bring it out to the middle there. This is way closer to 1/2, right? My y value is actually exactly at 1/2 than my x value. That is obviously not 1/2 for our x value. So that makes my y value 1/2 and my x value √3 over 2. Again, I can prove these values to you someday if you want. The other one is going to be the switch, the flip-flop of that. If I bring down my value here, my x value is at 1/2. And my y value is √3 over 2. And now these I can just reflect along my x and y axes to find the other values using my what I know is positive where. So here, this pi over 3 and 2 pi over 3 are the same. They reflect. My x and y values are the same, except for x is negative. So I have negative 1/2 √3 over 2. And then here, again, same situation, 5 pi over 6 and pi over 6. My x value is negative, so negative √3 over 2, 1/2. This is just how I remembered it and survived this long. Okay. Then you can take these guys and reflect them, or you can follow the lines here. If you follow the straight line, look at it that way, whichever way you prefer. I just like to reflect. So this one and my 5 pi over 6 and my 7 pi over 6, my x and y's are the same, except for they're both negative. So negative √3 over 2, negative 1/2. My 2 pi over 3 and my 4 pi over 3 are the same, except for they're both negative. So negative 1/2, negative √3 over 2. And then again, you can take these guys and reflect them. You can use these lines, or you can take your original guys and reflect them, whatever you like to do. Pi over 6 and 11 pi over 6 are going to have the same x and y values, except for y is negative down here. So I have √3 over 2, negative 1/2. And you can draw these lines if that helps you to see it. And then this one, pi over 3 and 5 pi over 3. My x is positive, my y is negative. So I have 1/2, negative √3 over 2. Couple other things that I just want to make a note of right here that we will use in the next section of notes. A, S, T, C. All students take calculus. Not necessarily true, and that's okay, but that's how it's stuck. All trig functions are positive here. Only sine and its reciprocal is positive in quadrant 2. Everything else is negative. Only tangent and its reciprocal are positive in quadrant 3. And only cosine and its reciprocal are positive in quadrant 4. So this is quadrant 1, 2, 3, 4.
What's the bottom one?
Calculus,
Cosine?
cosine, yes. The sine of theta equals y over r. R is your radius. The cosine of theta equals x over r. That is the y value of the coordinate at that angle theta. The x value of the coordinate at that angle theta. Tangent of theta equals y over x. Sine and cosecant, I'm going to write this word out so you can see what it is. Cosecant of theta are reciprocals, they're inverses. R over y, well, not inverses, but they are reciprocal. Secant of theta is r over x. And then cotangent of theta is x over y. So we're going to use these rules. We also need to know that, let's see if I need to know it right now. Yes, x squared plus y squared equals r squared. The x value, r squared is your radius. So r is your radius. X is the x coordinate at that angle theta. Y is the y coordinate at that angle theta.
What's like CSC?
CSC is cosecant, SEC is secant, and they're just opposite, they're reciprocated values. COT is cotangent, and we're going to use these a bunch. Stop recording here.